Hi, good morning. Welcome to another session of 10 minutes of learning. In the last video, we had promised that we'll discuss a little bit about the Lenz's law, which was a direct result of discussing about Faraday's laws of electromagnetic induction. So, in Faraday's laws of electromagnetic induction, quick revision, we saw that the EMF induced is equal to minus N d phi by dt, and we had talked that this minus sign is due to Lenz's law. Now, what is Lenz's law? Let us explain in this video. Now, we have taken this diagram to just demonstrate the simple concept of Lenz's law. So suppose there is a coil that you can see here. There is a galvanometer attached here. You have a bar magnet which was initially at this position A, B, and it has now been moved to C and D. That means the bar magnet has been moved in this direction from your right to left. So, due to the bar magnet being moved from AB to CD, the magnetic lines of forces associated with the bar magnet has been affecting the coil in such a way so that the galvanometer has shown a deflection in the right hand side. You can see here, considering it has started from a vertical position, it has now gone to this position, and a north pole has been induced at the face of the electromagnet. Sorry, a north pole has been induced in the face of the electromagnet. Now, how is this opposing? We talked about this sentence: effect opposes the cause. Now, how is this actually happening? Let us see that. So, the effect, what is the effect and what is the cause? The cause is the movement from AB to CD. This is the cause. This movement is the cause, and the effect is that a north pole has been induced on the electromagnet, which repels this north pole. This is also north pole, you can see here, and this north pole and this north pole, they repel each other. They do not attract, they repel each other. That means your movement from right to left is being opposed by the effect, that is the creation of north pole on the electromagnet, so that this magnet cannot come closer. Okay, in this case the EMF induced is in this direction. That means from the vertical position the galvanometer changes its direction to the right hand side. Now let us take the opposite uh, example. So suppose it was at C and D, and now it has started moving towards A and B. That means the movement is happening in the opposite direction, from left to right. What is happening? It suddenly comes to zero. The galvanometer suddenly comes to zero and then deflects in the completely opposite direction. That means in the left hand side. And what happens to the face of the electromagnet? A south pole is induced here, whereas it was north pole initially on the bar magnet on this side. That means there is a force of attraction. There is a force of attraction. Since it's going away, it is trying to attract. The effect is trying to attract the going away of the particular bar magnet. That means the cause is the going away, the effect is the attraction. Here the cause was the coming together, coming close, and the effect was the repulsion. So if you come too close, you will be repulsed. If you go away, then you will be attracted. That's basically your Lenz's law. Okay. I know some of you are laughing with this particular statement. Uh, yeah, so it's kind of that, whatever is coming to your mind. Uh, so this was all about Lenz's law. Now, how is this practically relevant, or how is this uh, utilizable in our study for rotating electrical machines? Let us consider on that. So I'll just take a very crude example of this particular diagram that you can see on your screen in a few seconds now. this is one of the very important diagrams that we need to consider to understand how the rotation of a DC machine or any rotating device works. Suppose you have your hand, you have your palm, right? So there are three fingers. The middle finger shows the EMF, the forefinger shows the field, and your thumb shows the direction of the motion. Okay, so it's like this. You can see here, this is the EMF, this is the field, and this is the motion. Now, if you keep your hand as a conductor. If your middle finger is showing you the direction of EMF, the EMF induced, and the field is the in this direction, that means from north pole to the south pole, then if your hand is the conductor and it is flowing EMF in this direction, that means in this direction, perpendicular to the direction of the field, then your hand will experience a motion or a force in this direction. It will try to go up. This will be the motion that is shown by this particular image. So from another angle, you can see that if your hand is kept like this and your direction of EMF is this, then it will understand or it will experience the direction of motion in the upward direction. Okay, you can obviously see that this is the direction of flux phi, and this is the direction of EMF E. So this will go up. Your thumb will try to move in the upward direction. So this is one of the major driving force, or this is the physical implication of how a motor works. Mathematically, we study this thing by something called dynamically induced EMF. Dynamically induced EMF, which is basically nothing but it is given by the EMF or the change in flux, which is dependent on the flux density, the length of the conductor, and the velocity of the conductor. That means this is B, or flux density. What is flux density? Refer to this diagram. So if you consider 1 meter square area, then whatever the flux phi is in that meter square area is the flux density. So theta per meter square, or this is also known as Weber per meter square. Okay, or this is known as Tesla T. The length of the conductor. It's simple. Length of conductor given in meters. SI unit is meters. And finally, the velocity of the conductor. Velocity of the conductor. That means whatever the displacement is happening. Now, this displacement is of two types. It is in meters per second, obviously. Displacement is of two types. One is straight, that is continuous. I'm sorry, that is in a straight line, and another is rotation. Okay, in both cases, the velocity of the conductor, which it can be also further subdivided into dx by dt. That means where x is the displacement of the conductor. Displacement conductor in meters. Okay. So the displacement of the conductor over a period of time gives you the velocity of conductor, and this particular dynamically induced EMF is given by E equal to rate of change of flux. This is from electromagnetic induction that we came to know. This is also equal to BLV, or BL dx by dt. Okay, so this is one of the expressions which govern the rotation or the EMF required. Now this goes both ways. That means if you give an EMF to this conductor, then what experience force it will experience, that is given by this expression. Okay, and if you give the force to this conductor in the presence of the magnetic field, then what EMF it will experience will be given by this. Okay, that means this is a bilateral equation. This is a bilateral equation working for both motors and generators. For motors and generators. Also, because if you give a force in the presence of this B, that means if you give this velocity, sorry, if you give this velocity to the conductor from some external means in the presence of this magnetic field, then an EMF will be produced. So that is the working of a generator. But if you give EMF as input in the presence of this magnetic field, you will get the velocity of the conductor either in static straight line form or in rotational form. You will get the velocity of this conductor, which implicates the working of a motor. Okay, so this equation is a bilateral equation which works for both motors and generators. As I was telling you, this is the foundational bedrock of the working principle of a motor and generator. Now we'll discuss the actual workings of motors and generators in the next video. Thank you. Leave your comments or feedbacks as in the below section. Okay, bye bye.